All right. So this is going to finish up our module on symmetrical components. And the part we're moving forward now is we're going to focus after this is now we have the ability to calculate fault currents. For the most common types of fault our power system will see. For the rest of the semester, excluding all the exam stuff, we're going to look at some of the basics of protection. There's way more power system topics to cover. Like we've been alluding to a little bit of unbalanced fault protection, unbalanced system analysis, which is far more complicated and really requires like a lot of keeping track of data because again, every bus is going to be a 3x3 network because you've got to keep track of all the impedances. And so those systems get really big and cumbersome. But for what we're trying to do, this does a really good job of explaining the concepts. And again, no matter what, if you have an unbalanced system or a balanced system, you can still use symmetrical components to make a determination about, do I have a fault current that is going in this location, or do I have excess load or something like that? So let's take another example, and this is just a simple 3-bus system. And now again, we need to really focus on the connections of the generators and the transformers and even the loads, right? We really need to see, is there ability for zero sequence current to flow through our system? Don't worry about the transmission lines because the transmission lines are not grounded. Now, some can argue saying there is some capacitive effects to ground on transmission lines, but we're trying to make this somewhat realistic and not, where we have to do real intensive analysis. So most of the time in industry, as well as here, we don't have to worry about any capacitive effects to ground. Because that's one of the questions you may ask is, hey, what about our pi equivalent? We saw those capacitors going to ground. Why don't we include them here? Because it doesn't really change our results that much so that we can ignore them. If you do have some underground cable, then that would be a different scenario. And the only difference is you would drop a capacitor here to ground. So all a capacitor is at the end of the transmission line is a load, right? If you move it to the bus location where the end of the line is, you can just show it as an actual load. And since that is a fixed impedance value, you can incorporate that into your Y bus, right? So since this is fixed, that becomes negative J X sub C. You can just add that into your Y bus. That's the self-admittance. So it's not hard to do. It's just that what we're going to try to do is simplify that because building Y bus is cumbersome enough. So we've got a 3-bus system with 2 generators, and each of the generators are grounded Y. And right now it shows that they're solidly grounded, right? So we don't have to worry about that. Then we also see that our first transformer going between the leftmost generator and bus 1 is grounded Y on both sides. On bus number 2, we have a grounded Y delta, and that connects to, again, that other generator that's also grounded. So pausing for a moment, just from a high-level inspection, is this system properly grounded from an electrical safety perspective? Does it look like this is a reasonable system? Anybody have any guesses or answers or throwing a dart at a board? No? Anybody know what throwing a dart at a board means? Unless you're a really good dartboard player or player darts. You're just doing this, and wherever it hits, it hits. You're just guessing essentially at that point. I know darts is becoming a bigger and bigger deal. That's why I add that in. But yeah, so one thing that's a little odd about this one is it would be very rare to have that as a grounded Y on that side. Anybody guess as to why? Why would that be grounded Y, and not delta then grounded Y?
Is it because it's an auto transformer?
No, it's not an auto. Auto transformers are pretty unlikely used for generator step-up transformers. And that's in my own personal experience. I've only seen a few auto transformer applications, and they're usually stepping up or down like at the transmission level. So it might be stepping up from like 115 to 345, something along that. And the reason why you don't see autos a lot for generator separate transformers is because you don't have electrical isolation. So if the generator is having a problem and it basically will feed current in, and you can actually get sky high voltages on your generator. So normally auto transformers are limited sort of for those applications when, hey, if our voltage goes through, it's not going to impact the rest of the system significantly because we've set our system up for that. It has to do with zero sequence isolation. Remember, this transformer right here, it looks like that, right? The zero sequence impedance for that transformer is like that. So if you have a fault over here, the generator is going to supply zero sequence current through the transformer. Which means if I have a protected device over here, we'll call it a 50/51N, which is a neutral overcurrent element, which monitors the ground current essentially. That is going to see that fault way over here. And if you're not setting it correctly, it could actually trip and remove the transformer before the device that's protecting that line takes the line out of service. So you've just complicated your coordination by a lot. If this is delta Y, then my configuration looks like this, right? Here's the zero sequence impedance for the transformer, and no zero sequence current flows from the generator from the generator through the transformer to feed the fault on the transmission system. So what you've done is you isolated the grounds. So that means I can have this one set to protect the generator side, and I don't care what's happening on this side of the transformer because there's no way for zero sequence current to flow. So I don't even need to coordinate. I ignore it. Makes things so much easier. And the typical ones, and this is where it's really wacky, but a lot of the stuff I've seen for setting overcurrent elements for pickup is like 1 amp secondary. Like they just pick one as like a nominal value. I don't know why. They just say, hey, one sounds like a good enough number. Let's go with one. That's a pretty common one that I've seen at the transmission level because they don't want it to be zero because any unbalance would cause it to trip. You don't want it to be the same level as phase currents because you shouldn't have any ground current on your transmission system. So you're going to try to find a happy medium. So ideally, that would be a delta. And almost every generator stepper transformer that I have is configured delta on the low side and grounded Y on the high side. Most utilities want that to be solidly grounded because it provides them a path or a reference to ground. I'm not saying in all cases, but in many cases, they want that to be solidly grounded. But for this example, and the reason why I chose this example is because I want you all to have to draw the sequence diagrams with different transformers. If I just had two delta Y transformers, you would just copy it over. So with that, I'll give you 5 minutes to draw the sequence diagrams because I said I'd like you to draw it. So 5 minutes, give it a whirl. Remember what you'll need, the transformer diagrams, and remember the positive and the negative sequence diagram. So draw all three. Maybe if you want to get motivated, you could do the positive or negative first, and then do the zero sequence last, because that's going to be the hardest one. But if you like to do the hard work first, then you can do the zero sequence first and then pick either the positive or negative to finish. just to get started, don't even bother showing the actual impedance numbers. Just show Z plus, Z minus. They're all the same, right? For the generators, transformers, and lines. So if you just put Z plus, Z minus, you should be able to figure out which is which. Give you one more minute. Let me clean up my mess here. Okay. Anybody get the diagrams for me? Anybody not sure how to do the diagrams? Few people? Okay. Which one do you want to start out with? Positive, negative, or zero? Positive, okay. If you can do the positive sequence diagram, that generally is almost the easiest one, but it tends to be exactly the same as a negative sequence diagram, except for the power supplies. So I don't care how the transformers or generators are connected, or loads for that matter. No care whatsoever, because in a balanced system, the neutrals have no zero sequence current. So whether it's connected to ground or not doesn't mean anything to me. So all I need to do is start drawing. This is XG. We'll just call it XG. This is XT. Now we've got our three buses. So this becomes X line. We'll call that bus 1 so we know which one it is. So we got the line in there between 1 and 2. Now I got to drop bus 3 over here. I have another line impedance here and another line impedance here. So I'm almost done, except I've got to now include the transformer and the generator that is connected over here. So XT and XG. And these are the pre-fault voltage. That's the positive sequence diagram. To show the negative sequence diagram, and I'll put kind of an orange color, it's exactly the same minus the power sources. Okay, there's no difference between the negative and the positive, except for the fact that the negative sequence diagrams has no power sources in it, right? And if I need to explain it again, I will, but there's no negative sequence power sources because the generators are producing balanced voltages. So if you had voltage sources in the positive sequence diagram, as well as the negative sequence diagram, you have zero chance of having a balanced system, right? Because that's the whole purpose of doing symmetrical components, is to break down unbalanced systems into balanced systems. So if I have two of those systems with power sources in there, that means without a doubt, I'm going to have an unbalanced set of phases. The last one I'm going to do is my zero sequence, and I'll do that over here. Now, this is the hardest one because I really need to be mindful of where the neutrals are and if things are connected delta Y. So easiest, I think, and this is the only one that I do it, I show a reference bus because this is the only one that I'm going to be showing impedances going to a reference bus or just kind of floating in the air. For positive and negative sequence, we know that the reference bus is internally connected because you have the three phases. Over here, you only have that zero sequence, and so all those systems are going to look the same. So the first thing we're going to do is we see, oh boy, we can come up through the generator. So that's good. And let me just double check to see, is there any neutral impedances on those? No. So we're going to come up through the generator. That's XG. Then we're going to go into the transformer. And because it's grounded Y, I have to blow right through the transformer. And one of the things that helps me when I'm trying to lay out where do I connect, you can see that I actually showed the bushings for the transformer. I'm actually showing the high side and the low side by indicating those are with bushings. So I'm showing two dots or two circles, whatever you want, to indicate that is one is the high side, one is the low side, or the bushings on the transformer. Because it is grounded Y, the zero sequence current has to flow through the primary side and flow through into the secondary side. Now I go to my transmission system, and this is where they get a little difficult to kind of go ahead and represent. This is bus 1. I'm going to put bus 2 up over here and bus 3 over here. Well, I want to erase. There we go. Now I have an admittance. Well, let me go ahead and swap that around. Let's call this bus 3 and this bus 2. So I have a line impedance here and a line impedance here. So I don't even care about delta Ys on the transmission system because there is no such thing as a delta Y, right? It's just a bunch of wires going from one side to the other. So I'm not connecting any loads. I'm just passing through the current. Do the same thing for here. And now I've got to look at my reference bus to see how things are connected. So now I've come to a grounded Y delta transformer. If you recall, the delta is going to allow zero sequence current flow in the Y winding because it can circulate around. We still are making sure that Kirchhoff's current law is valid. So we can have zero sequence current enter or exit the Y winding, but not the delta. So we put our transformer here. Again, dropping through. Oops, why can't I hit the button? There we go. And going to ground. And that's my high voltage winding, probably would be the secondary winding. Now the other side of the transformer is going to be floating in the air with no connection to the transformer leads because to the actual transformer windings, because no zero sequence current can flow in or out of the delta winding. But it can on the Y winding. So you'll notice I actually show the transformer winding, the zero sequence impedance transformer representation on the Y side, because that's going to limit current, because current can exit or enter the Y side of the transformer. On the delta side, no current can enter or exit, so I'm not even going to bother showing any impedance there. It's just going to be hanging open. Then I got to go through my generator or motor, and I have the zero sequence diagram. How many of you all got something that looked like these two?
Well, the new one connected to a class two, let's say X. What does that say?
This is X. These are the transformers, yeah.
Okay.
And the only reason why I call them XT is because if you look over here, the transformers have all the same impedances, generators, lines, so I just made it consistent. Okay. Now, these are all going to be equal to 1 at an angle of 0. Why are they equal to 1 at an angle of 0? Because we've assumed an unloaded system, and the pre-fault voltages throughout the system are all 1 at an angle of 0. So the internal voltages in the machine are 1 at an angle of 0. They match the terminal voltage. So that was my big first step, right? My step one was draw the sequence diagrams. Big first step. Yes, sir.
Small question, when you're labeling XP, positive and negative frequencies and all phase speed and it has compensate on the field frequency.
No, I just call them the same. They're all the same impedances.
And is that included boxes still XL as well?
Yep, these are all XL. So if I'm trying to figure out fault currents, what does the problem ask? Well, I don't know. It doesn't say anything, but we're going to try to see if we can solve this problem for faults at any location. So step one, draw the sequence diagram. Step two, build Y bus 0, Y bus 1, and Y bus 2. Which you all are expert at doing those now, right? So you don't need me to do those. Is that confirmation that you don't need me to do those, or you feel like you need to see those? Because we've done a lot of Y buses at this point. You're probably experts at it. Yes, no? Does that mean you need me to do it, or you want to do it on your own? You want 5 minutes to do it? That's the definition of repetition, is you doing the work. I already know how to do these. Yeah, 5 minutes. Do your Y buses. I'll zoom out a little bit so you can see them all. But Austin brought up a good point. Repetition is the key. Who's the repetitor, right? It's good English, right? The repetitor. I don't know if that's the right word. Repetitionist? Repetitioner? I don't know. Yes, sir. Well, just for now, just write XT, XL, and XG. Right, because they're all the same. And then you can substitute them in at the end. Again, it's better to work with variable names because then you can actually see where they come from. If you start putting in numbers, you're like, where'd that go from? Because they're all added together and you kind of lose that information. That's why in engineering, how many equations or problems have you written with all you see is variables and no numbers? Because it's easy to walk through the problem just by looking at variables. The numbers just get lost. One more minute. All right, what do you got? Anybody want me to put my work up there, or does somebody want to put their own work up there? Who votes for a classmate to put their work up? Who votes for me? Oh, I get a vote? I guess not. All right, so let's just do positive and negative, right? Because if you look at the diagram over here, we see that Z plus equals Z minus in every case. So there's no reason to draw two separate Y bus, right, two separate Y bus because they're going to be the same. So for positive or negative, our Y bus is going to be equal to, I'm going to factor out the J. The sum of the impedances connected at bus 1. So 1 over XT plus XG plus 1 over XL plus 1 over XL. Any questions on how I did the self-admins for bus 1? Is that a yes or no? Everybody's looking, but I don't know if that means they get it or.
You're good.
Okay. Anybody have a hard time with what I did here? Why
Can you
did I
scroll
write
up a
out-
bit so I can just compare it to the?
Right here is the positive and the negative sequence diagram, right? It's right next to it, or to the left.
Oh, gotcha.
The zero sequence is right above it. We'll do that one next. Anybody have an issue? I did 1 over XT plus XG and not 1 over XT plus 1 over XG. Do you have an issue with it?
All wrong.
Yeah, why? They're in series, right? So when you do Y buses and you invert them first and then add them together, that's the same thing as adding them in parallel. These are not in parallel with each other. They are in series. So you have to add them in series first before you invert, which is what I did. But the 1 over XL plus 1 over XL, those aren't exactly in parallel, but they're not in series for sure. So we can treat them as just regular old adminces. So then I subtract minus 1 over XL, minus 1 over XL, symmetrical matrix, and I'm good to go. Next one, bus 2. So I'm going to do the same thing. And now I've got my row 2, column 2 matrix. My last one is bus 3. That's Y bus. Anybody else get this? Good. So let's do the 0 sequence Y bus. My J out over here. So for bus 1, I can see what's connected. It looks the same, but these are 0 sequence impedances, not positive and negative. So XT plus XG. I would normally, if I had an impedance associated in the neutral, I would have to put 3 times that impedance below the XG, but we weren't given any ZN value, so we'll just assume that there's 0. Plus 1 over XL, plus 1 over XL, minus 1 over XL, minus 1 over XL. Okay? Just like positive and negative sequence. My next one now, I'm going to go to bus 2, and you'll notice this is where this value that isolated from bus 2 is something that I have to be really cognizant of, because for bus 2 now, I have 1 over XT plus 1 over XL plus 1 over XL. That XG has no connection. It's infinite impedance. And interestingly enough, the XG value doesn't show up anywhere in the Y bus because no current can flow through it, right? No matter what happens, if I put a fault on bus 2 or on bus 1 or bus 3, there's no current going through there. So why would the impedance be in there to help, provide a path for current to go there if it's not connected? So XG does not show up on bus 2. And lastly, that was step 2. Anybody get the 0 sequence Y bus? Close? Okay. So now our step 3, because we have all those, invert Y buses, find Z buses. Now it depends on the next question, which is find bus fault current for the fault type. And you can do this for any fault. It can be 3-phase, it can be single line to ground, it can be line to line, or it can be 2 line to ground fault. So I don't know exactly what we're going to be doing. You can do all of them, right? You can go ahead and do all of them, but you're going to find the fault current. 3-phase fault, you just look at the positive sequence impedance and pre-fault voltage. Single line to ground, you take the 3 sequence diagrams, the 3 sequence diagrams, the Thevenin equivalents of those, put them in series with each other, and then calculate symmetrical components. Line to line, you take the positive and negative, put them in parallel. Double line to ground, you put all 3 in parallel, and then you solve for your sequence components that way. So the step 4 has a lot of sub-steps below it. It just depends on what we're trying to do. So let's see what we're trying to do. Okay, so here's our positive and negative. Here's our 0 sequence, exactly as we've shown it. Now we have a positive sequence diagram. By the way, where is the fault that I'm trying to do here on the system? Can you tell? Can you tell where the fault is by looking at these 3 sequence diagrams? I don't tell you here, right? So where am I doing this work to solve for the fault current? Can you tell? Anybody? Do I not have enough information? No, I'm saying which bus is gonna be, I'm trying to do the analysis for. Because I have these three sequence networks. They're simplified down a lot. Can you tell which bus I'm looking to see the fault current at? Bus one? Anybody else say bus one? Who says bus two? Who says bus three? Who says I don't know? Fair enough. I love doing polls. Makes it so much more interactive. This forces TV land. All right, TV land. Please vote. So how many here said bus one again? Raise your hand. 1, 2, 3, 4, 5, 6. Wide, is that a hand raise or a scratching? Who says bus two? One, who says bus two? Who says bus three? Nobody? So there were like 5 voting for bus one, 2 voting for bus two, none voting for bus three. I forgot to ask, your guess is as good as mine. Anybody vote for that? All right. Nobody else is going to do the poll. This shouldn't take that long. 5, 4, 3, 2, 1, time. So it looks like if you add in-class guesses for bus one, it'd be bus one is the winner. Right? Very disappointed. Nope. What about bus two? That was the next big winner. Very disappointed. I have 2 votes, one for in class, or else he's doing the 3-pointer sign in the NBA. Right, he's Steph Curry. 2 people who are voting for bus three. Why are the bus three voters voting for bus three? I'm not saying they're right. I'm just asking the question. Nobody wants to answer. Well, did you just flip a coin a certain number of times and it came up heads enough? You said, okay, bus three. I will tell you why the correct answer is bus three. Look at these impedances here. 0.175, 0.175, and 0.1866. So the impedances that show on these network diagrams are the Thevenin equivalent impedances seen by that bus. Let's go up to positive sequence and negative sequence diagram. Do you happen to see a Z bus or Thevenin equivalent impedance that matches 0.175? Remember, we're looking at the diagonals. Those are the Thevenin equivalent impedances. What bus do you happen to see that on? Bus three. How about the 0.1866? Do you see that over there as well? Hopefully that's on the same bus position. Is it the same bus position, which is 3? Yeah, so this is trying to calculate a fault at three. Okay. So now let's look for a single line of ground fault. Take the 3 sequence networks, put them in series, which means now we just have a really easy KVL loop. 1 at an angle of 0 divided by the sum of the impedances tells me I get negative J 1.86. My positive and my negative and my zero sequence currents are the same. So I end up with negative J 1.863. Now I can solve for the positive sequence voltages, right? Just by doing the superposition approach. That's what we're seeing there. We're injecting this current, which is the positive sequence current, not the A phase current, but the positive sequence current. So we get the changes in the positive sequence voltage there. We do the same thing over here. Why am I not subtracting 1 at an angle of 0 there? I have 1 at an angle of 0 minus or plus the Z bus, right? Why don't I have 1 at an angle of 0 plus Z bus over here? Sort of. I think you're on the right track, but let me just put this up real quick. Oh, come on, wake up. Because remember my positive sequence diagram, this is EA, this is IA1, Z1, and this voltage over here was VA1. That's the voltage across the positive sequence network or diagram. The negative sequence, Z2, IA2, plus to minus VA2. So if I just do a KVL loop around that, isn't VA2 just equal to negative IA2 times Z2? So there is no 1 at an angle of 0. And I do the same thing for Z3. So I got my V negative, that's the change in voltage. I don't have any value there. And then I do the 0 there. Now, because of the single line to ground fault at bus 3, now I can get all the updated voltages. At bus 3, I've got VA, VB, and DC. At bus 1, I have 0.4522 at bus 1. Then I have those two numbers there for bus for B and C. And I would do the same thing for B2. Okay. And these are all these voltages that I'm calculating over here. Remember, these are for phase A. So if I want to go ahead and get the voltages at bus 3, I have to take the phase A voltages at bus 3. So these are VA at bus 3, and then multiply those through. And once you have this, now you can start calculating currents between the buses. So just like we had with the positive sequence diagram, now we have V1, V2, and V3 after the fault has occurred. Now I can calculate the currents flowing through the line. Because I have the phase voltages, but I also have the symmetrical components. So remember how we did Ohm's law way back on test 1? This voltage minus this voltage, V1 minus V2, divided by the impedance between them is going to give you the current. This impedance is all the same. So all you have to do is subtract the symmetrical component voltages, from each end of the line, and then divide by the symmetrical component impedance. This is the actual line Z, not the Y bus or the Z bus line, but the actual one. So if you're trying to figure out for coordinating purposes, I want to make sure that I coordinate my zero sequence currents for a fault at bus 2, and I don't want bus 1 and bus 3 to see that fault and isolate lines 1 to 3, for example. Then I would go ahead and do the coordination this way. So you're doing superposition all over again. You're just doing it with sequence current. Pausing to see if you understand what we're doing here, because we're trying to just be very consistent. It's always superposition, right? It's always adding in that post-fault voltage to see what ends up happening. And then continuing on from there. This one was a little bit easier. We could have made it much harder, because all three of these were the same. If it was a different type of fault, then this value here would not be the same as that one, right? You may not get the same symmetrical component currents flowing through there. But for a single line of ground fault, they're all the same. So it's no big deal. But remember, this right here is IF positive. This is IF negative or zero. No, negative. That's actually negative. Sorry. That's negative. We need to make sure that we're going through those so that we can see, yep, these all check off and we're using the right currents and the right sequence diagrams. Okay. Everybody bored, confused, not sure where to go? Because it's pretty important to really keep track of housekeeping here. We need to make sure that we have our housekeeping in place to order all these currents in. Fortunately, if you use an analysis package, it'll do it for you, like Aspen One-Liner, Power Tools for Windows, CAPE, SIME. All those programs will keep track of them for you. You don't have to do it. For us, it's hard to do much more than a 3-bus system because it gets more complicated to keep track of those things. But a few years ago, we had a senior project group, and they did a load flow of a blueberry processing facility in Cherryfield. And they wrote all the load flow program by hand. They just did it in MATLAB. And they had, I don't know, pages and pages of code because they didn't use while and for loops to kind of simplify the process. They just did it one at a time. And so they had a heck of a time keeping track of things because, you know, they just couldn't set up a for loop that would automatically do it for them, or a while loop. But if you set it up correctly, it's pretty easy to go ahead and do that. Okay. One of the last things we'll talk about is if you have a fault, it's unlikely to occur on a bus. The line is 50 miles long, 60 miles long. So it's more likely the fault is going to happen someplace out on the line than inside the bus, where you've got, you know, good vegetation management. You usually have pretty good rodent control, keeping animals and stuff out of the substation. If you go around some of the distribution substations, you've seen 2 fences now. You'll see the outside chain link fence, and then on the inside, you see the danger, you know, the yellow ones. And I don't know if those voltages are lethal, but I don't want to check to see. They're more for design for like livestock. It's like horses and cows. I mean, it puts out a pretty big shock. It would be much more painful if you were to come into contact with it. So you don't get a lot of squirrels and stuff like that. You can get birds and whatnot, but usually birds don't have a fault to ground. They usually would be a line-to-line fault. So it's unlikely going to have a fault at a bus. Way more likely going to have a fault on a line. So now we have to do all our analysis for faults on a line. But the problem is, where do we do that? Well, the sneaky thing is we just put a dummy bus. So we go back to our system here, and instead of having a 3-bus system, we do a 4-bus system. And that 4th bus is where the fault occurs. So we're going to have to rebuild Y-bus with that dummy bus put in there. It's a dummy bus, not because it's stupid, but because it actually doesn't exist. But from a perspective of building Y-bus and calculating fault currents, it's a real bus from the perspective of actually calculating those. It looks like a real bus. The system doesn't know it. So it actually has a perception of a Y-bus. So we'll put one at bus 4, and we'll put it a third of the way down the line. So we'll just break the impedances up 1/3, 2/3, and then we'll rebuild Y-bus. Here's Y-bus. Yes, sir. Ah, excellent question. How do you decide where to put the dummy bus? Any guesses? I can tell you what I've done. I don't know. So what I do in Aspen, it's really easy to do. You actually have the bus vary from almost up to the end of the line to the beginning of the line. And so you move it up in steps. Like I'll have the bus go from 1% to 99% of the line length, and I'll just run 100 different faults. And then I'll see which is the worst case one. Sometimes if I'm trying to get real precise, I might actually figure out where if there's a change and there's a protective relay operation change, and I might go 0.1%. I've even gone 0.01% if I'm trying to get exact fault currents. You usually look at exact values when you're trying to look at fault detectors to help with that. So generally you don't know. So what you do is you pick the worst case for coordination and you got to run through the whole line. So that's a really common one that you do in Aspen. I've never done it in Power Tools for Windows. Like I said, that's not a program typically based for utility systems. So it doesn't really have the same, it's going to be a wire. And so they're less concerned about that. But if it's transmission system, you're a lot more concerned with out there. I don't know, like Cape probably has the same capability, and I have no idea what SIME does. I'm not sure. I haven't used it enough to know. So this one, we just picked it, but again, you can do 10%, you can do 5%, you can do whatever you want. And you should do it, all those different ones, to make sure you've got all your worst case coordinations covered. So now we have a 4x4 matrix for positive sequence, negative sequence, and zero sequence. We're just going to show the positive sequence because now it's just busy work. Now that I know you're really experts because we were repetitious, right? We saw that example, and most of you all said you got pretty close. So bravo to you, right? Nobody here said they didn't get it. So I'm assuming that you're all being honest with me, and perfect. So we got a 4x4. Now we just have to go and figure out what the fault current is going to be for a fault at the dummy bus, which means I need that impedance right there. That's where bus 4 is. Even though there's no particular order, whoops, right? That's still at bus 4. So as long as I built my Y bus correctly, then it's going to shake out. I'll get the right numbers. So we've already talked about superposition. We did the pre-fault voltages. We've done all this all over again. Again, that's just a superposition approach. Here's one more example. You have a three-phase fault occurring with ZF. Now we're adding a fault impedance. So this is a simple one. All we need is the positive sequence diagram. But now we're going to add a fault at bus 3. Okay. So our ground, or I shouldn't say our ground, our fault is going to occur. And each one of those is going to have J.16. We don't have one single impedance there because this is a balanced three-phase fault, which means all three phases have to see the same exact value. So all three of those have to have that J.16. So we want to find the fault current, bus voltages, and line currents during the fault. So what do we need to do? We need the positive sequence diagram, step 1. Whereas before we did unbalanced, we needed all three. Step 2, find Y bus. Step 3, should say calculate Z bus. Step 4 is find IF. Step 5, update bus voltages. Oops, why isn't it writing? And step 6 is find line currents, right? That's the multi-step process to do that. So, whoops. Here's our, we don't even need to do positive sequence diagram. Do we need to draw it? It's pretty much right here, right? This is the positive sequence diagram. So we have our positive sequence diagram. You can even see we have the impedance in there. We build our Z bus. Now we're going to go ahead and add in our fault impedance here, not into our Z bus, because that fault impedance is not part of our system. It's only introduced there because a tree fell on the line, or I don't know, somebody did something. So we don't want to make that a permanent part of our Z bus or our Y bus. We're going to add it in at the end. Because when we draw our Thevenin equivalent, this is 1 at an angle of 0. This is Z Thevenin at bus 3. And then this is ZF. So that actually I'm going to grab from Z bus. The other one, I just put it in series. So my three-phase current just becomes negative J2. I update all the voltages. 0.76, 0.68, and 0.32. And now I calculate all of the line currents flowing. Positive sequence I1 to 2, I1 to 3, and I2 to 3. Anybody know if my answers are right or wrong? Can you look at this and tell me if they're right? I'm your supervisor. No, you're my supervisor. And I came to you and I said, hey, I got all the answers for the line currents. Here's my results. Do you fire me on the spot or do you keep me employed? And since we're at the university, we have to have for cause, right? So you can't just fire me for no reason. You don't like the clothes I'm wearing that day? Is it right or wrong? Is that correct? So I'm wrong? You're gonna fire me on the spot because I can't do math? Uh-oh, people are getting ready to fire me. Let me turn the tables because you even have a supervisor and you're ready to can me because I'm incompetent. So I'm like, supervisor, super supervisor. They said I was wrong. Super supervisor, where was the fault at? It was at bus 3. How much was the fault current? J.2. I have negative J 1.1 and negative J 0.9. Does that equal negative J 2.0? 1 to 2 doesn't help me at all. Doesn't help me check my work. It's what's going into bus 3. Does that equal the going out of? It's KCL. I can't use 1 to 2 because it doesn't help me KCL. But 1 to 3 and 2 to 3 help me for KCL. Yes, sir.
You go 0.9 going from 2 to 3,
It could, but then I would need that current right there.
and that one heading, since it's negative, it's heading 2-1, which would join them on negative 1.1 going down. And that's true.
Say that again. I missed the first part.
You have your 1.1 and 0.9,
Yeah.
but you have 0.1 going to 2-1, so since those are equal experiences going from 1 to 3 to 2 to 3, that's showing you that other 0.1 going to the left.
Maybe the only problem is, oh yeah, it would in this case because these are exactly the same. So yes, it would because only they're exactly the same. So in this one very specific case, yes, that would be the case. But wouldn't it be just more effective to say super supervisor? KCL says this plus this has got to equal that. But you're right. If you really wanted to dig deep in this problem, you could be like, and doesn't it also verify this? So you really don't like your supervisor if you're saying, look how incompetent. I go all these ways and they still get it wrong. So yes, it checks out. That's what I encourage you to do on the exams. Check your work. It's not a big reach, right? To check this one. It's pretty, do I want to say obvious when you put it out there, or is that an unkind word to use? It's not meant to say you're stupid. It's just saying to me, when I add it up, like, oh my God, it's KCL. When did you learn KCL? First years? Maybe even high school? So here's the summary, right? If you want to do it for double line, single line, I'm not going to do those because the work gets really busy and gets confusing. I used to do that in the past, but it gets to be so cumbersome, people just get lost as to what you're doing. But if you are interested, you can go to the godfather of power systems analysis, and Anderson. He passed away a few years ago, but it's a really good book that has a lot of detail and it's written sort of, more classical way. So it can be kind of hard to get through. You can also look at this Heidi Sadat's power system analysis, which is a more current version, but doesn't have widespread adoption. And then that's how you can check that out. Okay. Feeling better? Feeling worse? In the middle? Everybody's saying yes to all three, right? I feel better, worse, and in the middle, all at the same time, which is okay. You still have, what, a week and a half to feel better about this before the second exam or the third exam? I already posted the details right on the exam. Exactly as the class voted. If anybody gets upset about the exam being right after we get back from break, we live in democracy, right? Sometimes that's good, sometimes it's not good, but it's what the majority wants. Yes, sir. That'll be a review, yep. That's the plan.
For the lab that we did on. We got the,
Yeah, it's just the optional lab, yep. It's not even a requirement. If you want to do it, great. If you don't, there's no obligation. Anything else? Well, we can't do a lab next, well, we won't do a lab next week because I won't be around. The week after that is the test. And then we may do a study session that last week classes, but then that's it. All right, if there's nothing else, have a wonderful day, y'all. And we'll see you soon. Take care, everyone.